So let us get started now. So I had shared a video for the previous lecture where I discussed about the release of water from storage in a confined aquifer and how um, the water is released from storage by a combination of the compressibility of the aquifer and the compressibility of water. So what actually happens is that the aquifer actually gets compressed a little bit and the water expands by a little bit to just come out of the pores, and that is the process by which water is removed from storage, specifically in a confined aquifer. So uh, that's the classic difference between how a confined aquifer behaves and how an unconfined aquifer behaves. In the case of the unconfined aquifer, the the predominant mechanism by which water is released is by drainage by gravity, right? Whereas in the confined aquifer case, the process that removes water from the pores is by a combination, as I said, of the compression of the aquifer, which rearranges the pores of the soil particles into a more compact form, and the water expanding by just a little bit. And since the aquifer is not highly compressible, nor is water highly expandable, so to speak, so because of that, the quantum of water that is obtained by release by this mechanism is extremely small, which is why the storage coefficient of a confined aquifer is 1,000 times or 10,000 times or sometimes even more smaller than the specific yield of an unconfined aquifer. So this distinction is extremely important, and I also showed a few pictures of the implication of this excessive pumping, which is land subsidence, right? As the confined aquifer keeps getting compressed and compressed and compressed further and further and further, what it's doing is basically over a long period of time, over a substantial amount of time, the land surface actually starts to subside because the aquifer is getting compressed underneath, right? And so the extreme example, of course, is this the San Joaquin Valley in California, in central California, where extensive cultivation dependent on groundwater has happened over decades, and as a result, as you can see, you have land subsidence uh, uh, happening to the extent of tens of meters, right, or close to 10 meters or so, right? Massive subsidence. Okay, so I hope this phenomenon is clear. If there are any questions, now is a good time to ask. You can of course also ask on Friday, but uh, if there's any pressing questions, we can handle them right away now, and then we can take more questions on Friday. Any questions on this? I mean, I'm assuming that you guys watched the video. I didn't check the views. Well, I could have done that. Did everybody get to watch the video? Or did most of you watch the video? I don't know.
Sir, video is showing, sir.
Sorry?
Video is showing.
No, no. This video, or I don't understand. Video is you guys received the video, the YouTube video that I sent, right? Okay, somebody has to speak, please. Anyone?
Yes, sir.
Okay.
We received the videos.
Okay. You guys watched it also, I'm assuming. So anyway, so if you have not watched it, then it becomes difficult to discuss this any further today. So anyway, so if you haven't, then I strongly recommend that you please watch that video before Friday's class at least. Or I mean, of course, you can watch it as many number of times as you want, because it's going to be available for the rest of the semester. But my suggestion is that you watch it as soon as possible, so that if you have questions, we can have a discussion on Friday on this, and then we'll move on. Okay. So now, one question that often you know, is a little confusing to a lot of people is, why doesn't the same thing happen in an unconfined aquifer? Well, now the interesting thing is that it does happen in an unconfined aquifer, but the magnitude of that is so small that we, for all practical purposes, can ignore it, right? So if you look at an unconfined aquifer, there also there is the intergranular stress, there is the pressure, which is also holding up which is resisting the overall stress from the overburden, and so on. But the significant difference is that in the case of the unconfined aquifer, if I add some water, now when you add water, you can easily visualize this happening. If the water table is present at a certain point, I add some, what happens? The water table just immediately rises up, right? So, which means if I do the opposite, the water table will immediately go down. Now, the water table going up and down is the first reaction of the unconfined aquifer. So that comes from specific yield. That is the portion that is specific yield, right? This other process is also happening, but it is so insignificant. Before this process even happens, the drainage from gravity happens much faster, right? And therefore, in an unconfined aquifer, for all practical purposes, right? So just look at the size of this term: 10 power minus 3, 10 power minus 5. That is this term. And then this term is 0.05 to about 0.3. If you add a 10 power minus 3 to this, it will become 0.051. Not big difference. Or 0.301. If you add 10 power minus 5, it's 0.05001, whatever it is, right? Or 0.3001, something like that. So you get the number is pretty much controlled more by the specific yield, because the water is at atmospheric pressure, and when you add some water or subtract some water, the water table responds. Whereas in the case of the confined aquifer, the potentiometric surface is somewhere, right? The water is kept under pressure, and the potentiometric surface is way above the top of the confined aquifer, right? So the drainage by gravity cannot happen in the case of the confined aquifer, right? The only process that can remove water from a confined aquifer is this compression of the aquifer matrix, the soil matrix, and that expansion of the water by a tiny little amount, right? So that is the only process. That the same process also plays in unconfined aquifers, but it just is so insignificant. We would stop pumping much sooner. We don't even have to go to that extent, where the unconfined aquifer responds at a very in a more obvious manner, and therefore you would stop pumping before you would see the impacts of land subsidence and so on and so forth in an unconfined aquifer. And unconfined aquifers are also they also the time scales of responses are a little bit slower than an unconfined aquifer, confined aquifer. So, which is why I've given this analogy. Unconfined aquifer is like channel flow, and confined aquifer, the analogous, because pipe flow and channel flow you guys understand much better, right? So if there's a pipe flow happening, if I put a hole in a pipe at one point, okay, just imagine this. Suppose I have a pipe which is carrying some water, and I make a hole in one point, okay, immediately at the other end of the pipe, you will start to see a reduction in pressure. Most of the water will drain out of the pipe, and then you will not get any water at the other end. But if I have a channel and there's a leak in the channel at one point, right, nothing happens. That leak takes out a little bit of water, but the majority of water just keeps moving along in the in the channel, right? So the unconfined aquifer is like that, right? The pressure does not propagate so rapidly through the unconfined aquifer. So if you so the analogous way of thinking about this is in a confined aquifer, if I pump here, the impact of pumping will be felt over a large area, over a long distance, very quickly. In an unconfined aquifer, if I the impact is present is felt only in very nearby. It doesn't, the impact of pumping is not felt very far away. Okay, so that's the exact analogy that you can give for channel flow versus pipe flow. So like I said, in a pipe flow, if I make a hole in the pipe which starts to drain water, immediately the pressure in the entire system drops. The entire pipe drops, even if the pipe is hundreds of meters long or maybe even a kilometers long. The pressure in the entire pipe propagates so rapidly. Whereas in a channel, in an open channel, when I say channel, I mean open channel. If there is a small leak in one portion of the channel, it doesn't impact the rest of the channel. So the same thing with unconfined aquifers. You pump at one place, the impact is localized. In a confined aquifer, you pump at one place, the impact is felt throughout the aquifer. Anyway, so that's the kind of analogy that you can use to understand the difference or the differences between a confined and an unconfined aquifer. Okay. All right. So now what we're going to do is solve a few problems using. Yes, go ahead.
Yes, sir. Yes,
Is
sir.
there a question, Shantanu?
Sir, actually, I am joining late because I am sleeping. I taking the sleeping pill last 10 days. That's why. Sorry, sir.
No, don't worry. No problem.
Okay, sir.
No
You go
issues.
ahead, sir. If any doubt arises, I will ask. Definitely.
Fair enough. So the recording will be available soon. So I'll share the
Thank you, sir.
recording. So the first 10 minutes, of course, you can watch it again, and then you can.
Thank you, sir.
Okay, no problem.
Thank
Yeah.
you, sir. Thank you.
Okay, so let's move on. So we will solve a simple problem, and which will give you an idea of the uh, the volume of water that a confined aquifer will release and an unconfined aquifer release. Everything else being the same, just the nature of the unconfined aquifer and the confined aquifer, how they differ vastly. So I'm going to request that you guys solve this. Let's do the unconfined aquifer first. So it has a thickness of 10 meters. It has a specific yield of, oh, specific yield should not have units. I'm sorry. Let me get rid of that. Okay, is it visible again? Yeah, okay. So
Yes, sir.
the unconfined aquifer has a thickness of 10 meters, has a specific yield of 0.1, 10%. There's a head decline in the entire aquifer. Now, this is a little bit of an exaggeration. Heads don't decline uniformly throughout the entire aquifer, but for the purposes of this problem, let's assume that the head is declining uniformly over the entire aquifer. The head decline is of about 1 meter. The plan area of the aquifer is 10 kilometers square. How much water is released in the case of the unconfined aquifer? Can we just quickly calculate the volume of water released? How do you find out the volume of water released? You just have to go back to your definition of specific yield. What is specific yield? Specific yield is volume of water released per unit area per unit decline, right? So 0.1 specific yield equal to, maybe I'll just 0.1. Oops, sorry. Volume, I just said VOL divided by plan area, which is 10 kilometers square. So that's 10 to the power 7 meters square. I apologize for my handwriting. And there's a head decline of 1 meter. Right. So this is the definition of specific yield that we studied maybe one or two classes back. right? It's the volume of water released per unit area per unit decline in head. So in this case, the plan area is 10 kilometer square, which is 10 into 10 power 6 meter square. So that's 10 power 7 meter square. And the decline in head is 1 meter. So what is the volume of water that is going to be released? It will be 10 power 6 meter cube, right? So this is 10 power 7 meter cube and then multiplied by 0.1. So the volume V is 10 to the power 6 meter cube. Oops, sorry. Okay, so in the case of the unconfined aquifer, it is going to release 1 million cubic meters of water. Keep that aside. Now let's look at the second problem. I have a confined aquifer with a specific storage of 10 power minus 4 meter inverse. The thickness of the aquifer is given 10 meters. The head decline is 1 meter, same as before. The plan area of the aquifer is 10 kilometers square, same as before. So what is the storage coefficient? S is again the volume of water released V per unit area per unit head decline, right? And what is S? S is simply SS into B, thickness. This thickness is nothing but the capital B. And we define S as the storage coefficient or the storativity as specific storage SS multiplied by B. I'm sorry about this. My mouse pointer is not behaving. Okay, so SS is 10 power minus 4 multiplied by 10. So that's 10 power minus 3. So here I have 10 to the power minus 3 equal to the volume divided by 10 power 7 meter cube, right? Meter square multiplied by 1 meter. So that also gives me meter cube. So the volume of water release will be 10,000, 10,000, 10 power 4, right? 10 power 4 is 10,000, 10,000. So the volume of water released by the confined aquifer is 100 times less. Yeah, okay. So I'm not going to try and write this. Somehow it's, let me, okay, fine. So everything else being identical, only difference being the storage coefficient, you get 100 times more water from an unconfined aquifer as compared to a confined aquifer for the same head decline for the same plan area of the aquifer, right? So that indicates to you how different the behavior of a confined aquifer is from an unconfined aquifer. So that's something that you have to keep in mind when you look at this phenomenon. Okay. All right. Let's move on. Any questions before we move on? Okay. I'm assuming there are no questions. Yes. I didn't hear you.
Yes, sir.
Yes, go ahead. Question.
No question, sir. Go ahead.
Okay. Thanks. Let's go on. Okay. Now this is a very typical kind of problem statement where there's a lot of description provided in the problem statement, and it is your job to convert this paragraph into a picture. Okay, so it becomes important to be able to convert this understanding that you get from reading this paragraph into a conceptual picture. So let's read through this. Drilling data in a city indicated the presence of unconfined and confined aquifers below. Okay, very good. Water level in the unconfined aquifer was 3 meters below ground level. Okay. Drillers also found an aquitard 10 meters below ground level. Okay. Further drilling indicated an impervious bedrock at 30 meters below ground level. BGL is below ground level. Okay. Conductivity of the aquitard is 0.01 meters per day and its thickness is 1 meter. Piezometric measurements in the lower confined aquifer showed that the head in the lower unit is 25 meters above the bedrock level. Find the amount of water leaking via the aquitard if the area of the aquifer is 10 kilometers square. Also find the direction of flow. Okay. So now what this problem is forcing us to do is, unless you draw whatever has been written here, unless you convert this into a picture, it is impossible to solve this problem. Right? Because everything is given in terms of words. It is, I mean, the same problem. If I show you the picture and ask you to tell me what the direction of flow is, it's child's play. You just look at it and say, this is the direction in which the water is flowing. Of course, to find the amount of water, you need a little bit of calculation, but the difficulty in this problem is in converting this image, I mean, this paragraph into an image that can help us solve the problem. Okay, so that is what you have to keep in mind. Okay, so now the first thing I'm going to do is I'm going to draw the land surface. Okay, I might try to use different colors to indicate different things, but let's say this is my land surface. Okay, some minor ups and downs. Okay, drilling data in a city indicated the presence of unconfined and confined aquifers below. Water level in the unconfined aquifers was 3 meters below ground level. Okay, so now let me use a blue color ink to indicate the water table. Okay. Okay, I'm trying to draw it parallel to this, but it's not perfect, but I hope you understand what I'm trying to do. Okay, so this distance between the land surface and the water table in the unconfined aquifer is 3 meters below ground level. We are going to assume that this 3 meters is kind of constant in the entire area, in the entire city. Okay, so will this ever happen? Very unlikely, but let's just, okay, so this height is 3 meters. Okay, very good. Drillers also found an aquitard 10 meters below ground level. Now let me go back to the red color. So let's say it's over here. This is the top of the aquitard. Okay. Further drilling indicated an impervious bedrock at 30 meters below ground level. Okay, it's not going to be to scale, but okay, so this distance okay. Conductivity of the aquitard is 0.01 meters per day and its thickness is 1 meter. Okay, very interesting. So I'm going to make this aquitard 1 meter thick. Okay. Okay. So now I've got the entire picture more or less now. Piezometric measurements in the lower confined aquifer showed that the head in the lower unit, in the lower aquifer, is 25 meters above the bedrock level. Okay, so now again I'm going to use, maybe I'll use a different color for the this is the piezometric measurement. Okay, so this blue line is the water table, and this is the piezometric measurement, which is 25 meters above. So this is 3 meters, this is 30, so this should be 27, which means 25 will be below that, right? So it will be somewhere here. Okay, and this height is 25 meters. Okay, so this much effort has to go in before you can even start solving the problem. You have read 1, 2, 3, 4, 5 sentences and drawn this picture, and unless you do this, you cannot go ahead and solve the problem. Okay, so the blue line is the water table, the green line is the piezometric surface in the confined aquifer. The topmost line is the land surface. The next line is the top of the aquitard. The next one is the bottom of the aquitard, which is 1 meter below the top. And then the bottommost line that I show is the top of the bedrock, which is 30 meters below ground level. And so all of this information is given. Now comes the first question. Find the amount of water leaking via the aquitard. Before we get to that, let's solve the last problem of the last part of the question. Also find the direction of flow. So what would the direction of flow be? Upwards or downwards? Through the aquitard, there's some water leaking. Will it leak upwards or will it leak downwards? That's the question. How do we find that?
Upwards, sir.
Upwards?
Yes, sir, because of the atmosphere, the water pressure.
Because of the?
Water pressure, sir.
Okay, where is the higher?
Sorry, sir.
Is the pressure higher?
Sir, it will become more than atmospheric pressure, then the water will flow upward direction. If it is less than water pressure, then it go down due to the gravity.
Okay, so let us break it down first. Okay, is there any surface in this any point in this diagram where you know the atmospheric pressure, or where you know the pressure is atmospheric?
No, sir, it's not given yet. That's why it may be go down. But I not confirm. But according to my knowledge, I know that water will move upward direction because it more than the atmospheric pressure. So, sorry, sir, I don't know the actual answer actually.
That's okay. That's okay. Now, go back to the definition of the water table. What is the water table? The water table is basically a line that divides the unsaturated zone from the saturated zone in an unconfined aquifer. Right? So above the water table is unsaturated, below the water table is saturated. Right? So that's the first definition that we gave of the water table. Blue that you see is the water table. Then the next thing
below the water, sir, below the water table, the soil is saturated and also submerged.
Submerged. Okay.
And above the water table, the soil is unsaturated. Maybe some point of saturated due to the seepage. No, sorry, what is this? Capillary action.
Okay. Okay. But what is the pressure at the water table?
Below the water table.
At the water table.
Sir, at the water table, I thought it is neutral, like the strength of material, we know the neutral axis. I thought it may be neutral. I don't know it properly, sir. Such a
See,
nice, brilliant question.
you're using the word neutral in a very interesting way, and I mean, and your intuition is right. When you say neutral, you mean it is the background pressure.
Yes, sir. Very
It is neither
interesting
positive nor
question, sir.
negative.
Yes, sir. Yes, sir. That's a very interesting question. I don't also ever thought like that. That what is the pressure in the what at the water table, sir? Very interesting. Also, whenever you ask the
Well,
question,
if you go back two or
interesting.
three lectures or four lectures back, we actually said this in one of the classes. The pressure at the water table is atmospheric. The pressure
Maybe
below the
I
water
forgot.
table, yeah. So the pressure below the water
Yes,
table is higher than atmospheric, and the pressure above the water table can be lower than atmospheric if the soil is, partially unsaturated and so on. Anyway, so at the blue line is denoting the water table, and therefore the pressure at the blue line, the water table, by definition is atmospheric pressure. Okay. Now, this green line is an imaginary line. It doesn't exist apart from the fact that if you were to drill a well to the confined aquifer. Now let me imagine a well being drilled into the confined aquifer. Okay. Suppose I drill a well all the way into the confined aquifer, right? And the water, what will happen is the water level will rise in this well and come up to this point and stop here. Okay. So suppose I drilled a series of wells into the confined aquifer. At every point, the water level will come up to that green line, which is the piezometric surface. Now, what is the piezometric surface denoting? It is denoting the total head. The pressure plus elevation is the piezometric head. In the case of the water table, the pressure is atmospheric and the elevation is the height of the water table itself. Okay, so the
datum head or elevation head equal to 0.
no
Only the pressure head is the.
For the water table, you mean? For the water table, the elevation of the water table itself is the total head.
Okay, okay.
The pressure is 0 because it is atmospheric. It is the background pressure, the ambient pressure, right? The pressure
Yes, sir.
in the fine aquifer is greater than atmospheric. That's why the water level rises up and comes and stops at a point denoting whatever the whatever the pressure is. If the pressure was even higher, the potentiometric surface, that green line, would be higher, right? So this potentiometric surface, that green line that I've drawn, indicates the total head in the confined aquifer. The blue line indicates the total head in the unconfined aquifer. Now tell me, which of these has higher total head, the confined aquifer or the unconfined aquifer?
Unconfined aquifer.
Unconfined aquifer has got the higher head because the blue line is above the green line.
Yes, sir.
So now tell me, what will the direction of flow be?
Upward.
Flow goes from higher head to lower head or lower head to higher head?
A higher head to lower head.
Where is the head higher? Confined or unconfined?
The blue line is the higher head and the green line is the lower head.
Absolutely. So therefore, the flow will always go from higher energy to lower energy, or
Yes,
in
sir.
other words, higher head to lower head. So therefore, the
Yes,
flow
sir.
must be
Downward.
downward. That's correct. So the flow is downward. So we have solved the second part of the problem, which is a qualitative answer. We don't know the quantum of flow, but we already know the direction of flow. Just by drawing this figure, we have been able to figure out that the flow must be happening downwards, right? So that is like half the problem is done. Now we have to do the other half of the problem, which is asking us find the amount of water leaking via the aquitard. So now we'll have to apply some equation which allows us to figure out how much water is flowing. So now how do we find the quantum of water? How do we find the quantum of water? Well, the only equation that we have learned, pretty much the only equation we have learned up to this point is Darcy's law, right? So we have a head gradient.
Yes, sir.
We have a head gradient. The head gradient is across this
Q.
aquitard. Yeah, go ahead, Shantanu.
Q equal to, I thought KIA.
Correct.
I is head loss by length of the aquifer, I, and
Correct.
area of the cross section is given.
Correct.
And K is the permeability, or here we can say.
Okay, one second. You have to be careful. Now, this area of the, you said area of the cross section. It's not the area of the cross section. It is the area of the plan area of the aquifer. Right? Because
Yes,
the
sir,
flow
sorry,
is
sir.
happening in this direction. I mean, from top to bottom, right? So the area is always perpendicular to the direction of flow. Like think of the area as the area is always perpendicular to flow. Direction of flow is downward, so the area has to be in a plane that is perpendicular to this direction of flow. Whether it is upwards or downwards, the area is the plan area, not the cross section area. Okay, so Q equal to KIA, very correctly said, minus KIA to be precise. Okay, of course the negative doesn't make any sense because we already know what the direction is. So even if we get a negative answer, we already know that the flow is going downwards. So the negative sign really is has no practical significance in figuring out the quantum of flow. But in any case, let it be there because we have anyway we have used that. Oops, sorry. Okay, so what is K?
Hydraulic conductivity, 0.01 meter per day.
It is the,
we have to convert it first.
Converted to what?
Second or
Why?
minute maybe.
No, you don't have to. You can have
Yes, sir.
flow rate in meter cube per day also, right? There's no need to convert it. I mean, you can of course convert
Yes,
it.
sir. Thank you.
You will get an answer in seconds or minutes or hours or days. I mean, years, whatever you want to.
Sorry, sir. I thought it is a.
No
Sorry,
problem.
sir. Thank you, sir.
No problem. Don't worry. Okay. So K is obvious. It's given already in the problem. A is obvious. It's given 10 kilometer square. There you have to convert it to get it into meter square. So it will be 10 power 7 meters. 10 power 7 meter square. Now this I is interesting. What would I be? I is the head gradient. The gradient is across the aquitard. What is the head difference between the unconfined and the confined aquifer? What is the head difference? The head difference is this height between the two, right?
Yes, sir.
So that height is how much? Somebody quickly tell me.
2 meters, sir.
2 meters. Thank you. Okay. So I is
2 meters, sir.
Yeah, 2 meters divided by how much?
Length of the
It's the gradient across the aquitard. This head gradient is acting across the aquitard, right? The head above the aquitard is 3 meters below ground level. The head below the aquitard is 5 meters below ground level. So the head gradient is actually, strictly speaking, you should say -2. Well, you can say 2 also, it doesn't really matter. And what should the distance over which this head difference is acting be? Would it be easier if I mentioned it in this format? Now
maybe 1 meter if it is not given, 4 unit length will, if we calculate, the length will be 1 meter if we calculate 4 unit length.
per unit what? But where is this head gradient acting? That is the question. I think the confusion is arising because people are not able to visualize over what distance is this head difference acting.
Sir,
Yes.
actually, it is towards the board. It is towards the board. We could take 1 meter or 1 unit or whatever the unit taken.
You mean perpendicular to the board?
Yes, sir, perpendicular to the board.
Wait a minute. What is the direction of flow?
Downward.
Onwards. Okay. And the gradient must be the same as the direction of flow, right?
Yes, sir.
I cannot have a gradient in one direction and a flow in some other orthogonal direction. If the gradient is perpendicular to the board, then the flow also should be perpendicular to the board. But the flow is acting downwards. So there are two orthogonal planes. So the gradient, if the flow is downwards, then the gradient should also be downwards. Okay. So
yes, sir.
Let me try putting it in a slightly different format. So let us say I'll take the point at the top of the aquitard as 0.1 and at the bottom of the aquitard as 0.2, which is where I'm measuring this I, the gradient h2 minus h1 divided by z2 minus z1. Okay.
Yes, sir.
So now what happens is, what is the total head at 0.1? What is the total head at 0.1? The total head at 0.1 is the pressure at 0.1 plus the elevation of 0.1 at that 0.1.
27 meter.
27?
From the ground level, the blue line.
No. Wait. Yeah, it is 27 meters from the ground level. That is correct. But the question I'm asking is, what is the pressure at 0.1? 0.1 is just at the top of the aquitard. The pressure at 0.1 will be atmospheric pressure plus rho g h. If this is h.
If we take in gauge pressure, then only rho gh.
It will be only, but it's better to take atmospheric pressure because you know that will help in this particular problem. So just take it. Well, I guess you could do it either way. That doesn't really matter. But anyway, so it is P atmospheric plus rho g h. H would be 7 meters, right? Because blue line is 3 meters from the land surface and the top of the aquitard is 10 meters from the land surface. So therefore, this h will be 7 meters. So it's rho g h 7 meters. But is that the total head at 0.1? No, the total head at 0.1 is the pressure head at 0.1 plus the elevation head. Now the elevation head, we can use the bottom bedrock as the reference point, and then it would be what would it be? It would be 10. How much would it be? It would be at a height of I'm getting a brain freeze here. 20. It would be 20 meters up the bedrock. Is that right? I think, yeah. 0.1 will be 20 meters above the bedrock. So at 0.1, the pressure will be P ATM plus rho g h, where h is equal to 7 meters, plus divided by rho g, of course, right? PATM plus PATM plus rho GH divided by rho G. So it will be PATM by rho G plus 7 plus, what did I say? 15? 25, 5, 10. Yeah, I think it'll be 20. I'm sorry. It'll be 20. So assuming the bedrock to be, the top of the bedrock to be the datum, point 1 will be at an elevation of 20 meters above the bedrock. Point 2 will be at an elevation of 19 meters above bedrock. Okay. What is the pressure at point 2? What will the pressure at point 2 be? Now here you have to understand something very very important. The pressure inside the confined aquifer is same everywhere. Only the elevation changes. So if this point 2, if I pick it here, or if I pick it here, or if I pick it here, the pressure will be the same, just like a pipe. When you, if you have a pipe, the pressure inside the pipe at any given cross section, whether you put a hole at the top of the pipe or at the bottom of the pipe, the pressure at both points will be equal. Pascal's law, pressure is independent of direction, right? So the pressure at point 2 is the same whether point 2 is at the top of the aquifer or the bottom of the aquifer, or any point in between. But Z will be different if I move that point. Right? So therefore, you will have to figure out.
Yes, sir.
You'll have to figure out what the pressure at point 2 will be. How do you figure that out? It will be, how will you figure it out? It is these many meters above the height, above the top of the. How much time do we have? We have a couple of minutes. Let me quickly finish this. It is these many meters above the top. What is that height? 25. It's 6 meters above that, right? It will be, the pressure at this point will be inside the well. The pressure at this point will be atmospheric. So if I come down 6 meters, the pressure here will be PATM plus rho G into that height H. Right? So then if you do all of this messy calculation, you will end up with a height of 2 meters. I will leave that as an exercise. Anyway, we'll meet on Friday. We'll again go through this. The distance over which this gradient is acting. Now that I've picked the points 1 and 2 at this point and at this point, you know the distance between these two. Z2 minus Z1 is 1 meter. Right? So K is known. The head gradient is 2. It is 2 meters divided by 1 meter, the distance over which that gradient is acting. And the area of cross section is also given. So you put in all the numbers in there, you will get the flux Q going through the aquitard. And as I said, we've already just figured out what the direction of flow is. Okay?
Okay, sir.
So
Sir,
we will, yeah.
I have a question.
Go ahead.
Apart from this study, sir, when do you come to college? And we will see
Friday
you
we are meeting in
offline.
person.
This Friday, offline class.
This Friday.
Thank you, sir. Thank you.
This Friday we'll meet in person. Okay?
Thank you, sir.
Yeah, I'm also looking forward to it. See you guys on Friday. Take care. Maybe I think I'm already over time. Yeah, with just a couple of minutes. Okay, just take a look at this problem statement, think about it, and then come back. I'll share the slides with you. I have a circular island in the middle of a lake. The radius of the island is given. There's a confined aquifer in this island. The initial head in that confined aquifer is 5 meters. The thickness of the aquifer is given. The hydraulic conductivity of the aquifer is given. The lake level, there's a lake surrounding this island, is also at 5 meters above some, with respect to some datum. I place a pumping well at the center of the island and I start pumping. Okay. At steady state, the water well is 2 meters above that datum, whatever it is. what is the pumping rate in the well? That's the question that I'm posing. Think about this problem statement. Think about how you can solve this, and we will discuss this and of course the previous problem as well in Friday's lecture when we meet in person. Okay, so thank you very much. Take care. I'll share the slides and the video, and then we will have a discussion on Friday. Take care. Thanks a lot. See you all on Friday.
Thank you, sir. Thank you.
Yeah, bye bye. See you all in person on Friday. Please come to class.